Hi, my name is Muhammad Rizwan Qayyum, doing Mechatronics Engineering from National University of Sciences and Technology, Pakistan. I am here to present my paper on wood defects classification using GLCM based features and PSO trained neural network. So let's start. Introduction. Wood industry is one of the biggest industry all over the world, but the prospects are not brighter either. Local manufacturers are facing problems due to import of cheap materials that has many defects in it. Moreover, the importance of wood cannot be ignored in many aspects of life. Quality of wooden products is heavily dependent on wood strength. Presence of defects such as knots may reduce the wood strength. Elasticity and stiffness of the wood plate are the important properties that are also affected from strength perspective. Manual inspection is a slow process. Moreover, it does not guarantee 100% inspection. Machine vision based inspection systems are in great focus nowadays. They are capable to save inspection time by quick or timely detection of defects, thus improving the reliability of quality control process. The paper presents a strategy in view of a PSO-trained feed-forward neural network that takes texture features as inputs and classify wood defects. Gray-level co-occurrence matrices. Gray-level co-occurrence matrix GLCM is one of the effective techniques for texture feature extraction. 4 GLCM features were computed from grayscale images: contrast, correlation, energy, homogeneity. Proposed algorithm: a feed-forward neural network trained with the particles from optimization algorithm. The algorithm guarantees fast convergence. Neural networks, with their remarkable ability to derive meaning from complicated or imprecise data, can be used to extract patterns and detect trends that are too complex to be noticed by either humans or other computer techniques. A trained neural network can be thought of as an expert in the category of information it has been given to analyze. 4 features are used as inputs: contrast, correlation, energy, homogeneity. Network architecture: feed-forward neural network. Neuron configuration: 4 input layer neuron, 10 hidden layer neuron, 3 output layer neuron. Defect classification as dry knot, horn knot, and sound knot. Algorithm flowchart. Figure shows the flowchart of the proposed technique. The technique uses 4 distinct GLCM features that are energy, contrast, correlation, and homogeneity for a feed-forward neural network. The training algorithm utilized for this purpose is particle swarm optimization algorithm. The algorithm first generates random weights for the network. The objective function of PSO is the mean square error (MSE) of the neural network. On completing the maximum number of iterations, the algorithm chooses the best weight values against a fitness function. The final weights are then used by neural network to classify wood defects. So, firstly, GLCM based feature extraction. Then the data set is divided into training and testing subsets. Then initialization of neural network weights and biases. Then inputs are loaded to neural network. Then PSO parameters are initialized. Then set trained neural network weights as initial particle position. Then set network MSE as fitness function of PSO. Then update P-best and G-best according to fitness value. On completing the maximum number of iterations, The algorithm chooses the best weight values against a fitness function. Update weights and biases according to G-best, which is also the global best. Then, neural network response was tested. Experimentation. Standard dataset of wood knot defects available at the website of University of Oulu, Finland are used. The dataset contains 90 images of wood knot defects, 3 defects conditions: dry knot, horn knot, sound knot. Experiments are conducted for 3 types of wood knot defects: dry knot, horn knot, and sound knot. The specimen for each knot defect is shown. Firstly, the specimen for dry knot. Secondly, the specimen for horn knot. And thirdly, the specimen for sound knot. The complete dataset summary. The table shows the mean and variance for contrast, correlation, energy, and homogeneity values of each type of defects. Plot of contrast and correlation values for 90 defect images. Dry knot is shown by blue circles, whereas green and red circles show the data for horn and sound knots. Plot of energy and homogeneity values for 90 defect images. Dry knot is shown by blue circles, whereas green and red circles show the data for horn and sound knot. You can see the variation between energy and homogeneity values for each defect type. %70 of the whole dataset is used to train the neural network. 30% of the dataset is used to test the performance of the trained neural network. The response of the neural network is shown here. Class 1 represents dry knot, class 2 represents horn knot, and class 3 represents sound knot. First graph is the response of neural network for training data. Second plot is the response of the neural network for testing data. The neural network response for the testing data is plotted in red line against the green line of the target data. Mean squared error (MSE) of the network is calculated as its fitness function. MSE becomes constant after 60 iterations and does not decrease further. Figure shows the MSE graph of PSO trained neural network. Results for wood knot defects. Mean squared error of the network is found to be 0.34834 for training data. Accuracy for testing data is 78.26%. Testing data accuracy is found to be 78.26%. The confusion matrix for testing data is shown. Here, C0 is for dry knot, C1 is for horn knot, and C2 is for sound knot. For dry knot, 3 samples out of 5 samples are truly classified and detected as dry knot, whereas 2 samples are falsely detected and detected as sound knot. Whereas for horn knot, 9 samples out of 10 samples are truly classified or detected as horn knot, and 1 sample is detected as sound knot in case of horn knot. Whereas for sound knot, 6 samples are truly classified or detected as sound knot, and 2 samples out of 8 samples are falsely detected and detected as dry knot. 78.26% accuracy for wood knot defects testing data. Conclusion and future work. A particle swarm optimization trained feed-forward neural network is used to classify the defects using GLCM based features, which shows promising results. Average accuracy is 78.26%. Future work involves investigation of other features and classification algorithms. Moreover, further exploration of AI-based techniques for wood knot defects classification also involves future work. Thank you.